Okay, so today I want to discuss a bit different kind of statistical models. Actually, let me use the terminology from machine learning. There are two different kinds of problems that are related to data analysis. In one problems, which are called supervised learning, we have some variable, like we have some variable y, and we want to predict this variable using some other variables. Actually, these problems of supervised learning lead to all regression methods that we discussed are supervised learning methods that allows one to solve supervised learning problem. So in this problem, you have some data, and in this data you have values for your variables, and you have a value for variable y that you want to predict, and you just try to find some law that allows you to predict these values using these values. And in linear regressions, these laws are just linear functions. We discussed some other types of regressions, for example, logistic regressions that provide some more complex models. But anyway, the problem is the same. You want to predict these values using these values. And when you create, in a sense, a good tool to predict, you can say, okay, I believe that my data were generated by the model that is close to one that I found, I fitted. And so I can make some conclusions about reality, about some processes in language or in any other kind of reality. I can try to explain them in terms of my model. So I can try to say that some variables affect some other variables and so on. So this is generally supervised learning problems. And we also discussed unsupervised learning problems, even without calling them by that name, unsupervised. And in unsupervised learning, you don't have any values to predict. You just have some data, and you want to uncover some structure in this data. Examples of unsupervised learning problems are dimensionality reduction, like methods that we discussed, like PCA. And there are other methods that allow you to decrease the dimensionality of your data in different ways with different properties. Just to name a few, I can say that there is TSNE, UMAP, MDS, and some other. And another problem that we discussed that belongs to unsupervised learning family. What problem? Who remembers? Which problem we discussed that also deals with the case when you don't have any values to predict, but you have some data and you want to uncover some structure in this data.
Hierarchy.
Hmm?
Hierarchy. Hierarchy.
Yes. Clustering. Yes. Some clustering problems, including hierarchical clustering. Yes, that's correct. So methods here are like k-means, hierarchical clustering, and many more. Here we discussed so far regressions. And these regressions are a really useful tool, but sometimes it is not enough to deal only with regressions, because regressions assume a rather rigid structure of your model. In regressions, you assume that there is just a formula, usually a linear formula, that relates y and x. So y and x1 and so on, xn are related by some simple formula. And on one hand, this assumption is natural because this is what we are usually interested in. We are usually interested in a simple laws, like when x increases, y also increases. We are usually interested in models like this. But sometimes it is possible that you have some relation that it is difficult to describe by these kind of simple formulas. Either you have to include a lot of terms into these models, or you have to do some other hacks. Sometimes we need something else, something nonlinear, something that is not given by just a simple formula. And today we will discuss this kind of problems. So this is a big picture of methods that we discussed so far. If you remember, initially we discussed some tests like t-test or chi-square test, but basically all these tests can be considered as a version of regression models. So basically, for example, in chi-square test, we are asking a question like, is it possible to predict the value, some numeric value, based on some categorical variable that take only two values? So it is also can be seen as a supervised learning problem. And these problems are unsupervised learning. Actually, this subdivision came from machine learning field. Probably previously it was called in a different way. And actually there is some distinction between machine learning approach to these problems and some other approaches that are more close to other branches of science. Actually, generally everything that we discuss is mathematical statistics, but different fields of research use statistics in a little bit different way, and they focus on a little bit different things. For example, people from economics created the whole branch that is called econometrics, which is also can be seen as a kind of rebranding of mathematical statistics. But in this approach, we are interested in interpretation of these models. So what economists are interested in? They are interested in causal questions that allows one to uncover relations between variables. They want to give conclusions like, if I adopt such and such policy, then it will affect some parameters that I'm interested in this way. For example, if I adopt this policy, then unemployment will increase or it will decrease. And to provide such conclusions, we need to have some causal models, models that allows one to uncover causal relations and causal effects of different variables. So we want to say that, for example, I don't know, regulation of some regulation of some field will increase unemployment or decrease in unemployment. So this is some causal effect. And this is econometrics. And in machine learning, they're a bit more just straightforward practical approach. In machine learning, people solve most oftenly, they solve purely prediction problem. I have some values. I have some row in this table in which I have the values of X, and I just want to predict the value of Y. And these problems arise in a lot of real-world fields, and so this kind of problem became very popular. And in this approach, we are not care a lot about the model itself. The model can be considered as a kind of black box that gets the values of X and predict value of Y. How it is constructed, how it works, in machine learning, they do not, well, they say sometimes we don't understand how it works, but it works, we see it empirically, so it is good for us. There are slight distinctions between these approaches. And today, this was a long introduction, but let me introduce today's main topic. This is decision trees. And this is a model that belongs to this supervised learning framework, but it is different from regression model because it does not assume too much about the law that allows you to find Y using X. These decision trees are actually very popular tool in machine learning. They are not popular alone. They are popular as a part of some other algorithms like decision forests. But let us begin with decision trees. What regression model says in just linear regressions or models like them? We say, okay, give me these values of X, and I will put these values into some formula, and I will use this formula to get Y. In decision trees, a little bit different approach is used. In decision trees, we ask questions about our data, and when we are sure about answer, then we give this answer. So let me give you an example. Actually, decision trees can be run in different modes. They can be run to predict some numerical value like linear regression, and they also can be run in a way to predict some categorical value. This is called classification problem. Let me start with using decision trees in classification problems. In classification problem, we want to predict some category, some class. And this class is just a value of some categorical variable. So decision trees in classification problems. And let me begin with example. Assume that I have two-dimensional space and I have two classes. For example, I will get some classes like this, and I have some other classes like this. Okay. So this is my data. And let me put some numbers. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. How regression trees work? Regression trees try to predict. In this case, when we discuss about classification problems, they try to predict class of some item. And this class, in this case, this class can be either this circle or this cross. Let me use this these symbols to denote these classes. And how regression, how decision tree give you a prediction. Let me assume that I have some new point, for example, this point. And I want to predict the value of this point. I want to predict a class of this point. So these points are present in my data set, and this is a new point that does not present in my data set. And in this case, I can ask some questions about values of my variables and proceed like the following. First question, for example, is it true that x1 is less than 0? And then I have two possibilities. It can be either true or not. Yes or no. And after that, I can do one of the following things. Either I can give you a prediction, or I can proceed with the same question asking. So have you ever played in a game like I guessed an animal and you ask me questions and I answer yes or no to these questions, and you have to guess which animal I think about. So this is actually very similar, but instead of an animal that I keep in mind, we are trying to guess the class of this point. So we ask a question, is it true that x1 is less than 0? Let us look at the picture. How do you think? If answer is yes, then what will you do? Will you give an answer, or will you continue asking questions? What is your prediction? Or if you don't want to make a prediction, what is your next question?
Give an answer. If it's less than 0, then it's got to be from the circle class.
Yeah. We see that at least according to our data, if we are to the left from this line, so we are here, and we see that all items here are of red class. So probably it is reasonable to give a red class here. Okay, but if the answer is no, it means that we are somewhere here. What will be your next step? What will you do?
Is it more or less, is x2 more or less than 2?
Okay, we can ask another question. For example, is it true that x2 is less than 2? And again, we can get two possible answers, yes and no. Mm-hmm. Yes. So what if the answer is yes? So it means let us draw the areas that we processed so far. So we have this line. Use different color. We have this line, and we said that all these points are red. At least we will give this prediction. And then the second step is that we say if we are here, then we have to ask this question. So we have to draw this line. And again, we have two possibilities. What should we do? If the answer is yes, what should we do?
It's a cross.
It's a cross. We can make a prediction. And if no, if we are here, so it means that we are here.
If x1 is less than 3?
Mm-hmm. Yes, actually we can continue, but probably we can stop here. In fact, it depends on what we really want. On one hand, we can continue and we can ask another question, like for example, split it here. Okay, let us do it. So I want to split it like this, and this is done by a question like x3 less than 3, and I have two options now. If yes, then my prediction is cross, and if no, my prediction is circle. So let me put some colors here. This picture now corresponds to this decision tree. So if I have a new item now, I can put this item into this decision tree and get a result. For example, for this black point, I will be, if I have this point, I answer no here, then I answer no here, then I answer no here, and I'm here. So I will give you a prediction that it is a circle. So we say that all points from this area have to be assigned to this class. The prediction will be this one. So this is basically how decision tree works. If decision tree is constructed in some way, then it gives you some function that for each input values produce prediction. So are there any questions about this part?
If we cut something, for example, we draw the first line and the second line, в общем, учитываем, да, это.
Ну, как бы у вас,
она не вторая линия уже не пересекает первую.
Ну, да, имеется в виду, что вот вторая линия вот такая, а не вот такая. Ну, да, да, потому что как бы мы считаем, что вот если мы, вот как дерево работает, значит, если мы вот здесь ответили «да», то есть если мы находимся вот здесь, то мы уже дальше никаких вопросов не задаем и выдаем вот такое предсказание. Ну, стало быть, нас вот это вот следующее разделение, оно разделяет только оставшийся кусок. Значит, вот то разделение, которое соответствует вот этому. Ну, то есть теоретически можно было провести его целиком вот так вот, но просто вот эти две половинки закрашены в один и тот же цвет, поэтому вот эта часть нас просто не интересует. So if I draw this picture, it is reasonable to draw this line just in this part because only this part is processed by this arrow. But this arrow just processes all this half plane.
А там не должно быть x1 вместо x3?
Должно быть. Other questions?
What to do when the data is not that homogeneous, when you don't see this, I don't know, the straight where to put it? How do you decide where to put it?
Yeah. So we'll discuss now how to deal with the actual data. Actually, now when I constructed this example, I just wanted to show you how these trees work when they are created. But how they are created, this is another topic. We'll discuss it very soon. So actually, these decision trees, in a sense, mimic some reasoning process that we perform when we are trying to predict something. Actually, for example, if you have an expert, like for example, a doctor, and if they make a decision by looking at some data, for example, which medicine to administer, and they just look, for example, at information about a patient, and if you ask them how do they do their decisions, they probably can say something like, okay, first I see at this parameter, and if this parameter is in this region, then I will proceed in this way, and if it is in a different region, I will check another parameter, and if it is in this region, I will proceed in another way, and so on. So actually, these decision trees are a logical approximation to reasoning in terms of this question asking, and this is a reasonable way to think about relations in our data, if these relations, at least if these relations cannot be do not have such simple forms like linear regressions. So how actually these decision trees are constructed, and when they are useful and when they are not useful. First, constructing decision tree. Let me still consider these classification problems, but actually a similar algorithm can be applied to regression problems when you have to predict some numeric value as well. I will say about it a little bit later. So how to construct the decision tree? Assume you have, let me return to my example. Probably I have some other data. Something like this. So let us consider just a first cut, a first question that we are asking in our decision tree. First of all, we are asking questions that are of form like, is it true that some variable is less than some threshold? So to define this, this question, this predicate, you have to decide which variable to use and which threshold to use. And actually, you have just a finite number of variables, and you have just a finite number of possible thresholds, just because you have finite number of observations, and it is reasonable to consider only thresholds between two observations. And it means that you can just iterate over all possible ways to do it and decide which one is better. Our goal is to obtain as homogeneous parts as possible. Every choice of this splitting gives you two parts of your data set. For example, I put my splitting line like here. And I want my parts to be homogeneous. I want, for example, if I have just two classes, then in a perfect case, I have just a perfect splitting. All items of one class are in one part of my splitting, and all items of another class are in another part of my splitting. For example, if I put my splitting in a way that is shown in this picture, I see that on the left part, I have more or less perfect splitting. Perfect, this part is perfect. But this part is very bad because I have a lot of green points here and a lot of red points here. And I'd like to have, for example, if I have, I want all these points to be in just one class. In fact, I will use some ways to estimate how homogeneous my part is. So if I have, if we have a collection of observations of some items, we can define some impurity function or impurity criterion. Impurity function that says how far from homogeneity our collection is. For example, actually, people use one of two impurity functions. First, this is Gini Impurity. And this is a function that is defined in the following way. Let us assume that I have a collection of items of several classes, not necessarily two classes, but for example, it is possible that we have three classes, like this, this, and this. So we have three classes in this example, and Gini impurity is calculated in the following way. It is sum of pi times 1 minus pi, where pi is percentage of observations of class I. For example, here I will get something like this. If I equals to 1, let us assume that it corresponds to this class, and I have P1 4 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And if I equals to 2 corresponds to this class, then P2 is 2 over 13. And for this class, I have P3 equals to the rest, 1, 2, 3, 4, 5, 6, 7. And if you put these values into this formula, you will get some value. And it is possible to show that this value is the largest possible if you have more or less equal percentage of all classes. And for example, if only one class is present, what can you say about the value of this function? If, for example, I have here only green crosses, but 0 red circles and 0 these yellow squares. What can you say about the value of this Gini function, Gini impurity? If one of these values are just 1, what can you say about this? Mm-hmm. Yes, it is 0 because, for example, if all items are belong to this class, then P1 is 1, and all the rest are 0. And it means that in this formula, I will get 1 times 0 plus 0 times 1 plus 0 times 1. And it is 0. So if py equals to 1, and then Gini equals to 0. So, Gini is largest if P1 equals to P2 and so on pk. So if these percentages are just equal to each other, then in this case, this Gini is the largest. So this function is one of possible way to measure impurity of my data set of some class distribution. Another formula is another impurity function is entropy, and it is similar but a bit different. Entropy is given by this formula when you have this logarithm, pi times logarithm pi. And again, you have to make a summation. And properties are the same. If one value is 0 and if one value is 1 and other values are 0, then it is 0. And it is largest if all values are equal to each other. So both of these ways allow you to measure how impure your subset is. Are there questions about these things? So if I ask you to find Gini impurity for a particular distribution of classes, for a particular collection of objects for which we know they are classes, can you find it? Let us do a very short exercise. If I have, for example, if I have only 2 classes and I have this set, what is Gini impurity in this case? Can you give me a value? Mm-hmm. Yeah. Mm-hmm. So we just have to find P1 that is 1/3 and P2 that is 2/3. And then this Gini is P1 times 1 minus P1 plus P2 times 1 minus P2. And this is 1/3 times 2/3 plus 2/3 times 1/3. And this is 2 times 4/9. Yeah. Okay. So let us return to our problem. What you're how do you choose this predicate? You just iterate over all possible ways to do this splitting, and you minimize weighted sum of your values of impurity function for each part of this data set. So I have some subdivision. I have some objects here. And here. And I can find the following function. Q, it is a function of my predicate. So I and T. And this function is the following. Let me denote this part by L and this part by R. And then I can find something like this. Number of elements in L times your impurity function of L plus number of elements in R times impurity function of R. So here number of elements. And EF is impurity function. Gini or entropy. And I want to choose the value of this Q. What do I want to do? I want to minimize or maximize this value. Do I want to minimize or maximize this value?
Minimize.
Yes, I want to minimize because my impurity function is small if my parts are very close to just a homogeneous part. So I want to minimize it. So that's all. I just iterate over all values that is interesting to consider. And for each value of my threshold and for each variable, I just choose, I just find the value of this function. This is the quality of my splitting. And I just choose this splitting that provides me minimal value of this Q. That's all. And in this way, I described the first step, but all the other steps are done in the same way. So if I do the first step, then I can consider one part that is obtained from this step, for example, left half, and then I can apply the same algorithm to this part. So I can do it recursively. I just get a part and I subdivide it and get another part and subdivide it and so on. So proceed. After first splitting is found. Proceed with each parts in the same way. And this is how can we construct our tree. Are there any questions so far?
Yes, can we have not one but two things in this circle when we have a decision? So for instance, not just x2 is larger than 2, but x2 is larger than 2, but smaller than -2.
Well, theoretically, yes, you can, but people usually don't do it because you can do the same thing just by using two questions. You first ask question about one value of this variable, and then we ask question about another value of the same variable.
Yes, I had that idea, but before the moment of this splitting with the impurity function, because what if in the first part of my decision, or division, everything works, but in the other it doesn't?
Yeah, yes, I see. Actually, indeed, this procedure is not guaranteed to give you, in a sense, optimal splitting. It is possible that you have some other splitting, some other tree that will be better in a sense that you produce by this algorithm. But anyway, basically you can try to use to do something more complicated than this simple predicate. But in practice, I never seen that people do it. But basically in the literature, it is discussed. But I haven't seen it in practice nowadays. Sometimes people consider not this kind of questions, but the questions, like you said, when you consider not array but a segment, and this is called bump hunting, when you just find some bumps. So yes, it is possible, but rarely used now. Actually, now people do not use decision trees alone, and we will discuss why a bit later. So, other questions? Okay. Now let us discuss. Actually, I think there is a question. There is a natural question about this algorithm. Probably the answer seems to be too obvious to ask this question. So in a sense, I described some recursive algorithm, but I never said when we will stop. So we can split and split and split, and when we have to stop. And this is actually interesting and important question. Where to stop? First of all, it is clear that we can construct such a tree that in all that finally we have a splitting for which in each part we have elements of only one class. It is possible to continue until we have pure parts. Only one class in each part. This is actually what we did in this example. In this example, we produced 4 parts of our final splitting, And in each part, we have elements of the same class. So they are perfectly pure. And this is possible option. And in any case, you can do it, just because if you grow if you grow a tree with arbitrary depth, so arbitrary deep tree, then you can just split and split and split and split, and finally, if you just want to stop only when you have only one class in each part, you can do it, and you can proceed in this way. But it is not very good idea. Actually, to discuss why it is not a good idea, we have to return to our initial problem. What we are going to do, we want to construct some algorithm that allows one to predict the values of some variable, in this case, the values of class, based on some other variables, in this case, based on x1 and x2. But how can we predict? We understand that each point that generated that is obtained in our data is in a sense random point. If we think about this data as something that is empirically obtained from some experiment, we understand that it is possible that we have another data that came from the same source, and we wanted to predict values for this new data. And in this case, if we construct a tree that will be too complicated, it will perfectly describe the data that we have so far, but it will not be very good at predicting, because it is said that it will overfit. It means that it will rely too much on the data that we have, on all local properties of this data, and these local properties can be not presented in the general population. Assume, for example, that each point here is a person that can be one of two classes, like monolingual or bilingual. And assume that we have something like this. Assume that I have data like this. For example, this is age, and this is income. And I have this data. And I have some two classes, like these people are monolingual, and these people are bilingual. Oops. And what can we say about this data and about laws that can generate this kind of data? How can I just from from common, if I use just a common sense, what can I say about the relation between this variable and these variables? If I look at this data, what can I say? How can you interpret this data just from common sense without any statistical science? What this data says you?
Well,
Just give me some guesses.
Simple words, to me, it could be just an exception. We can use this term in statistics.
Yes, yes. Actually, we can say that in our data, we see that at some threshold age, people become bilingual. That all people are monolingual, but in this age, but most of people are bilingual at this age. But not all. We have this observation, just one observation, that violates our rule. How can we interpret it? Basically, if we speak about people, we can say, okay, there is one strange person who really does not follow the general trend, who is monolingual despite the fact that he or she is at this large age. We can think that this is not a general law, that people with this particular age and this particular outcome are usually monolingual. We can think that this is just a fluke, this is just an artifact of our data. We understand that it is possible for any individual person to be bilingual or monolingual even if they are here, to be monolingual even if they're here. But we see from the data that it is very rare. And if we see one person like this, it is not reasonable to try to extend this and to generalize this observation to the whole population. So it means that if I get some new person for which for who I know their age and income, and if I see that this person is somewhere close to this strange green person, what is my what is your prediction? How do you think? What is if you see this data? What is the better prediction for this unknown black point? Will you predict that this person is bilingual or monolingual? Sarah suggests to predict that this person is bilingual. Yes, actually, we can say that even despite the fact that this point is very close to this this monolingual person, we can say that, okay, we see this monolingual person, but it is just a fluke. We do not think that we have to take it into account in our prediction. We see a very strong law, a very strong trend that more or less all people whose age are larger than this threshold are bilingual. We believe that this trend is universal, even despite the fact that some particular point violate this pattern. And probably this prediction will be better than the prediction when we say, okay, this point is close to this green point is green, then this point is probably also green. So is it clear, this idea? This is rather important idea. Is it clear or not? So if we construct the deepest tree, this tree will create some part that contain only this item. So this tree will work like the following. I think that it will work like this, then this, for example, then probably this, then probably this, and then probably this. So it will assign predictions, red predictions here, 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 and here, and green predictions here and here. And we understand that this is not the best possible predicting algorithm, predicting function, because we understand that probably we just better to ignore this point rather than generalize this point to the points that are close to it. So if we construct the deepest tree, it can overfit. Overfit meaning that it will it will rely too heavily on the data, including all random flukes in this data. That are not generalized to population. So this is a very important notion, the notion of overfit. Actually, it does not correspond only to it doesn't correspond only to trees. It corresponds to any models. But when we discuss linear models, they usually do not overfit too much because they do not have enough parameters usually. Usually you have a lot of data and a small number of variables. And in linear models, you have only a small amount of parameters, a small number of parameters. And such models usually do not overfit because they cannot care about some local fluctuations of your data. But some local algorithms like decision trees can overfit, and they will overfit. And this is actually the main reason why trees, and especially deep trees, are not used much on the practice. So sometimes it is much better not to, actually most always, it is much better not to continue until we have pure parts, but to stop earlier. For example, in this case, it is better to stop after the first splitting and just give predictions like all green points here and all red points points here, just to ignore this green point. So we can predict. So we can stop early and use, for example, how to say it, the most popular class in each part as a prediction. So we can, for example, think about this part. This part contains elements of two classes, but the majority of these elements belong to this bilingual class. So we will predict at the whole part, we will predict this class. When exactly to stop, it is interesting questions. And in the model that is used in R, in C3 library for R, a special statistical criterion is implemented. It stops splitting when cannot reject null hypothesis that class does not depend on each variable. So we can do, for example, chi-squared test or some other tests, some other statistical tests, and test that our class depend or not depend on each variable in our data set, in our part that we are going to split now. And if we can reject, then we continue splitting. If we cannot reject, then we stop splitting and use this as our prediction. This algorithm limits the depth of our tree and allows to deal with overfitting, at least partially. So this is how these decision trees work. Actually, another problem with decision trees that they if they are too deep, then they overfit. And if they are not deep, if they're shallow, then they just do not have enough complexity in them, enough flexibility to create a good predictions. So basically, just a tree alone is not very popular tool. But one of advantage of just a single tree is that it is interpretable. We can just draw this kind of pictures and just look how our tree works, which variables it uses, and so on. But on practice, people use some other tools. Probably after the break, I will spend 10 minutes more to discuss these tools that are based on this decision tree algorithm. Are there any questions about trees so far? Okay, then we can make a 10 minutes break and then we continue. Let us continue. So, disadvantages of trees. Deep trees. With very large number of levels, overfit. And shallow trees. Are not flexible enough to catch interesting dependencies. So if you have shallow tree with small number of levels, then it means, for example, that if your dependency is like this, for example, something like this, this is easily catched by some model like logistic regression, because it can find, it can split your elements just by a straight line. But it is almost, if you have just a shallow tree, you cannot catch this diagonal line because you have only horizontal lines and vertical lines. So the best thing that you can is something like that you split it like this, then you split it like this, and then you split it like, I don't know, like this. So your splitting border will be something like this, that consists with vertical and horizontal segments. And it is impossible to catch this diagonal line with good precision if you have only a small amount of this of these splittings. So these are disadvantages of decision trees. Advantage of decision tree is that it, in a sense, interpretable. You can draw it and see how it thinks. Interpretability. And to deal with these disadvantages, we can use different methods that are based on trees. And I will present one method methods that use trees. Actually, two methods are popular. One is called random forest, And another is called gradient boosting. And let me discuss very shortly, very briefly, let me discuss this random forest. In this forest, we do the following thing. Instead of using one tree, we train a lot of trees. And all these trees are fitted using a similar samples that are similar to your original sample. Similar but not identical. So to construct a random forest, you have to do the following. First, construct many new samples from your original sample. Using a procedure that is called bagging. What is bagging? You have your initial sample. It consists of some rows. And this is our sample. And then we resample this sample. I mean that we select rows randomly with the replacement. What does it mean? I have a new sample. Assume that I have n elements here, and I will have n elements here. And I select first row in my new sample. I select as this first row of my new sample a random row of my original sample. I just select some random row here, random observation, for example, random person in my research, and I put it here. And then I continue the same thing with each row here. So for example, to create a second row, I again randomly select a row from this original table. It is possible to select the same row twice or more times. I just select all rows at each step. I select all rows that are present in my original sample with the same probabilities. So for example, on the next step, I select this row, but on the third step, I select the same row as previously. It is possible. And when I finish, it is possible that some rows are selected several times, and some rows we did not select some rows at all. So some rows are just skipped. So the set of all rows in a new sample will be not the same as the set of rows in the original sample. This is my new sample. So every row here is some row here, but not all rows here become rows in my new table. And this procedure is called bagging. I don't know why. I assume that it is like you have a bag of observations and you randomly select an observation from this bag, and you record it to this new table, and you return this observation to this bag, and then you shuffle this bag and again do it until you get the same number of observations here as here. Are there questions about this bagging procedure?
No, it's clear.
Good. So in random forest, first we construct many samples from our original sample. Then we grow many trees, feed each tree to its own new sample. So we can do this procedure a lot of times, and we will get different samples. And then we feed each sample to its own decision tree. And so we grow a lot of decision trees. Actually, there is some additional randomization involved. Just a second. We have some additional randomization. That I did not discuss so far. But the main idea is that we grow each tree with its own sample. And finally, when we want to make a prediction, when this forest that contains a lot of trees will make a prediction, each tree will make its own prediction, and then we aggregate these predictions of these trees. For example, if it is a classification problem like we discussed, we can make like a majority vote of these trees in our forest. So aggregate predictions. For example, by majority votes. So each tree in our forest make a prediction, and then we just say that prediction of the forest itself is the result of majority vote. Why this procedure is reasonable? First of all, are there questions about this procedure? Everybody understand how it works?
Yes, it is clear.
Great. So let us return why this procedure is reasonable, why random forest is reasonable. Let us return to this example. Let us assume that I will grow deep trees, that these trees cannot, that these trees can catch this item. But the idea is the following. When I create new sample from my original sample, this item can be either included or not included into my new sample. And if it is not included, then my decision tree is very simple. Like it is just one splitting and two parts. If it is included, then I have to proceed and consider more complex tree. But for a particular point, we have some probability that it will not be included into my new data set. So some of our trees for points that are close to this one will give us the prediction that we should predict red point here, and some will give us green point. The majority vote will be, at least it will provide not, well, I think that the majority of our trees will give us in this example, the majority probably will give us the same green prediction at this point particularly. But anyway, it is clear that this method allows us to remove these outliers in a sense and to consider like an averaging, like an averaging procedure that allows us to decrease the effect of these outliers of this kind. So this is an idea of this random forest. The problem with random forest is that you have a lot of trees, for example, 100 trees or 1,000 trees, and it is not easy to visualize the result of this random forest, and it is not easy to interpret it. But anyway, if you think about the quality of prediction, random forest will give you much better results than just a single trees, usually. So this is one method to use decision trees as a part of some algorithm that provide better results than just decision tree alone. Another method that is extremely popular now is gradient boosting. I don't have time to explain it in full details. Let me just give a general idea. In gradient boosting, you construct something in between of trees and regressions. In gradient boosting, you construct some sum. So like A of X, this is prediction at point X. Is created as a sum of some other algorithms, like A0 of X plus B1 of X plus B2 of X plus and so on plus BK of X. And usually B1 and so on, BK are decision trees. So this gradient boosting is it constructs some additive model, but use decision trees as part of this model. Of course, it is possible to consider this sum when we speak about regression problems when we're trying to predict some numeric value, but it is also can restate to deal with categorical problems at all, classification problems at all. So this is the story about trees. Actually, my main point about trees is that there are some models that are not limited to just simple formulas, that you can consider models that looks like we discussed here, that is completely different from a simple formula that just uses this question asking technique. And sometimes for some problems, it is possible to use these trees. Unfortunately, it is not possible to use them if you are interested in a relation like when X is increased, then Y is increased. This is the domain of just linear models or their generalizations like logistic regression. But if you are interested in some other questions, for example, if we know the values, some values, what is our best way to predict some other value without any restriction on how we do it, then decision trees and these models that are based on decision trees can be a good choice. So this is some distinction between classical statistical problems when we use simple models like regressions, and machine learning problems when we are mostly interested in just a good prediction. Are there any questions so far? We can probably discuss very briefly application of decision trees, not to classification problems, but to regression problems. Let us assume now that we have some regression problem. So assume that we have some data like you have X, you have Y. Now Y is numeric variable, and we have some points as usual. Something like this. And then we can create some decision tree. Of course, it is possible that we have more than one X, but it is easier to draw pictures if we have just one X. So let us do it. Now we can create some regression tree, like regression decision tree that will ask questions like this. Is it true that x1 is sorry, we have only one x, so is it true that x is less than 1? If yes, we can stop and give a prediction. For example, we have some values here, 1, 2, 3, 4. So we can split it like this, and we can make a prediction like we predict value 1 at this region, and then we can continue. If no, we can make another split. Like, is it true that x is less than 5? And then we can make another prediction, for example, 3. And finally, we can make a different prediction. For example, 2. So this is a possible tree for solving of regression problem. You see that instead of considering straight lines that take place when you do just a simple linear regression, regression trees consider functions that are piecewise constant. So it is constant at one segment, and it is constant at another segment, and it is constant on the third segment. So it is possible to apply our decision trees to these problems as well. Again, it has some limitations, but actually you can use this thing to approximate any functions you wish, just because any function, any continuous function can be approximated by these stepwise functions, constant, something like this. So it is also possible to use decision trees for regression problems as well. As a prediction, in this case, you just select average of values that you have in this part. As impurity, you can take variance of values in a particular part. You want to decrease variance as much as possible in each part. So this is how this algorithm can work. So let us look a bit at the code. I need RStudio now. Are there any questions so far about the theory that we discussed?
So we have two tools, if we can say just in general. We have these regressions and we have this tree making. And how to choose which one to apply to our data? Or
well, it more depends on your problem than on your data. If you are interested in questions like how change of a particular variable will affect another variable, then you have to use some linear models or their generalizations. Because if you have tree, you just have a prediction that is given by these questions. But if you assume that your relation is not linear, that if you assume that it is even not reasonable to expect that you have a relation like when x is increased, then y is also increased. If you expect that your relation can be something non-linear and and you are not interested in a particular interpretation of this relation, but you're interested in questions like, is it possible to predict some values based on another values? Is it possible to, or probably, which variables can be used to predict some value? Then you can use trees and you can use algorithms based on trees. So actually, when people solve problems that involve pure predicting, so for example, there is a website called Kaggle, and people on Kaggle solve machine learning problems. They get some data sets and they try to create an algorithm that allows one to solve this prediction problem, predict y's based on x's. And on this Kaggle, it is very popular to use random forests or gradient boosting, so algorithms that are based on trees instead of using regressions, because these algorithms can catch complex nonlinear relations, and they can deal with a lot of variables more or less automatically. And so they are, in a sense, much more universal than linear regressions when we are speaking about just a quality of prediction. But if you want interpretation, if you want to ask questions like, what happens with y if I increase x by 1? then you have to use regressions. And probably if you assume that your data, that in fact your relation is not linear, then you can, well, you can add more variables to your data to make it more close to linear. For example, if I have some side note about nonlinear relationships in linear models. For example, if you assume that your relation between x and y can be given by something like this, and you understand that you don't want to use linear regression for this model because you have different parts of your graph, and on one part you have increasing, and on another part you have decreasing. Then one way to do this stuff is to consider additional variables. You can consider a new variable like x squared. So we initially have table like x, y, for example, 1, 1, 2, 4, 3, 7. And then we can add a new variable x squared, and we have a new table. And in this new table, we have something like this. And then you can fit your linear model with this data, with these variables. And in this case, your relation is like beta naught plus beta 1 x plus beta 2 x squared. What is the graph of this relation, of this function? What happens if you add x squared here? Oh, the graph of
it shall be a line, one line.
Line, what kind of
No,
line?
it's this.
Yes, this is actually a quadratic function, and the graph of quadratic function is parabola. And parabola can be fitted to the data like this. It can be fitted like this. So this is one of possible graphs of parabola. So if you believe that your actual relation between y and x is like this, not linear but quadratic, then you probably can use this trick of adding of new features, of new variables, and stay with linear models. Actually, in economics, people use these relations when they discuss, for example, the connection between salary and age, because salary and age are connected in nonlinear way. At the beginning of life, your salary will grow fast, and when you become older, the growth rate decreases, and with some time, it can even decrease. So this is a good idea to consider this kind of quadratic relationship for these pairs of parameters. So sometimes you can just do these tricks and stay with linear regressions. Sometimes you don't want to invent these additional features, and you want just to put every data in your model and just let this model work. Then if you're interested in predictions only, if you're not so interested in interpretation, and you believe that it is possible that you have some complex interrelations in your data, then probably you can better to use decision trees. Actually, as far as I see from your projects, in some cases, in your projects, you have a lot of categorical data, and you can try to use trees with this categorical data, because actually we discussed in this lecture, we discussed examples when our variables here and here are numeric, but it is also possible to consider categorical variables and to make decision trees with them. And probably it is a good idea if you have a bunch of data and a lot of categories and a lot of levels, and you just cannot create a simple regression models. Probably you can try some trees and just look what they say. Probably it can be interpreted in some way. So let us try to do something about it. So, but probably you have more questions about the first part. Okay, then we probably can proceed. I need to share my hair. So I will use this data set now. So we have a data set that was collected by our former student Varvara Sveshnikova in her bachelor paper. And it is related to consonant drop. So we have different words like бесчинствовать, злорадствовать, and we are interested in a drop of the consonant, like do we have V in this word in pronunciation, and we have several categorical variables. So this is actually a lesion that we want to predict, and we have word, we have position, and we have group. I don't know what is group. Let me see. Group is just a group of words. Бесчинствовать, бесчинствую или бесчинство. Word is root under analysis, and position can be strong under logical stress or weak. So let us try to use the special function C3. Probably I have to install an additional package to do it. Let me try. I will use this library. However, some other libraries exist. So I hope it will install it. So it seems to be installed. Now we can use it. It is called party because we part our data at each step of constructing tree. And now we can use function C3 to make our regression, to make our tree. So C3, we need to predict how this variable is called V elision. And we predict it as a function of all other variables, group, word, and position. Data net. Let us store it in some variable. This is pretty fast. We can visualize this tree now. Yeah, so this is our result. And actually, this is the output as applied to categorical variables. For categorical variables, we can use not just to consider a threshold and split by threshold, but we can consider different subsets of each categorical, different subsets of levels of each categorical variable. For example, here we have group that can take 3 possible values, first, second, and third. And our tree used this variable and split it into 2 parts. And first part contains only items with the value third. And in second part, we have first and second. And here you see this visualization. We see that after this initial splitting, we have the second splitting. And in this splitting, we consider different variables at the second question. If we have this part, then we split by position. And we have this splitting. So we can say that for items in third group in weak position, we usually do not, we don't have this elision. So you can just see percentage of each class here. And here you also see the corresponding percentages. And here you see the p-values that are associated to null hypothesis that there is no dependency between the variable under consideration, this elision, and corresponding variables like this, like the variable that we consider as our independent variable. So in a sense, we can interpret this data in some way. So we see, for example, that the fact that we are in a strong position increases chances to have decreases chances of elision, decrease probability of elision according to this table, according to this graph. So this is our model. We can actually use this model to make some predictions. For example, if we have so we have function predict, and we can create. Let me create a very short data frame that consists with only one observation, and I want a new data frame that looks like an initial data frame, like this one, but I want only one row. And for example, I want data frame. Okay, let me see columns of my initial data frame. So we have, for example, group, third, we have word, for example, package, and position strong. And I will predict using my tree. I will predict new data. Level of factors of new data do not match original data. That's not good. Okay. I need to create a data frame with factors with the same levels as in the original data set. So I will construct them in this way. Probably it can be made simpler, but I don't know how. Mm-hmm. Now it gives me a prediction, just yes. So we can predict not only the result, but probably we can predict also probability. Let me try now. Can I predict probability? Just a second. I have to look at the documentation of this particular function, party predict. Probably. Type. Yeah. In this case, it gives me probabilities of each outcomes. They correspond to the levels of my variable. So it seems to be, I don't know, yes and no, or no and yes. It seems that the first result here is probability of getting no, and the second result is probability of getting yes, because this is the order in which we see the corresponding levels in my original variable. These probabilities just get it from the percentages of each class in our final part of our partition. So we see, okay, what happens with my prediction if I change this word. For example, if I replace this word from попечь to zlor. What happens in this case? What happens with this prediction? Let us look at the tree again. What happens if I change in my new item for which I want to ask for prediction? What happens if I change this variable? So I use this tree to make a predictions. And in my prediction, I put as my data, I put these values. Factor third, position strong, and I changed this word. What happens with my prediction? Any ideas? How this tree take into account this word variable? Yes, nothing changes, just because this tree ignores this variable. It is possible for a tree to ignore one of the variables because just we do this splitting until we reach our goal. But if we don't have this variable in these splittings, then we just ignore it. So nothing changes. Let us see. Yeah, the same results. Actually, we can print our tree just to look at it. So it gives us the same information more or less, but with text form. So interesting how to proceed, how to print this tree in a way that it gives some predictions. It seems that it is not possible. Okay. So are there any questions so far about this tree? You can try to apply this tree model to your data just to look what happens, and probably you will get some interpretation. Probably you get some grouping of levels of your variables, and probably it gives you some new insights. Okay, if there are no questions, let us look. Yes. Yes, sure. My tree is just a result of application of this C tree. And this syntax is very similar to the syntax of regressions. So I say that I want to predict this variable using these variables in this data set. Yes, we need party here. Hmm. So let us try to use random forest instead of single tree. Let us apply it to the same data. So I will use the same formula. It gives some warnings. So takes too much time for this forest. Let's try to tweak it to tweak some options in this forest function. Okay, something strange happens. Okay, I terminated R. Oops. Let me try it again. So I will use cForest again, but with special options that will make it happy. So this is cForest. And again, I use let us try this. And 3, this is called. Okay, now it worked. Actually, in this line, I set to my random forest. Actually, I set this variable mtry. This is related to the randomization that I announced but did not discuss. Actually, when we construct a random forest, we not only randomize the observations in our data set, but we also randomize variable to choose. So at every step, when we choose our threshold, we can select a variable only from some randomly chosen subset. So this is some additional randomization that makes everything more random. And to I don't know, it said something strange about these parameters mtry. So fixing it manually just makes this thing happy. So now we have this forest. Unfortunately, we cannot visualize it. We can use it to predict something. For example, I can predict for some, let us pick some row from my data. Oops, no. Like, let us consider this second row of my data and find the prediction of my forest for this row. So I feed to my forest and my observation with this data. So I can do it in this way. It doesn't like my prediction. I don't know why. Probably we have to put some. This is predictions of each tree. So we see that some of my trees created answers yes, and some created answers no. I see. No, this is probably predictions for my initial data. Sorry, I'm not sure that I understand what are these predictions. But these are just prediction for each row in my original data set. These are predictions of my forest. But probably I want to. I don't understand why we cannot feed. A particular row. I don't know. Another way to think about forests is to draw, to find information about variable importance. So it gives you some information about how important each variable in our prediction. There are different ways to do it in random forests. As far as I remember, this function shows you it do something like this. If you include this variable and if you exclude this variable, the quality of your prediction will change. And importance of a variable is how worse our prediction quality becomes when you remove this variable from our analysis. So you probably can use this result, this variable importance, to analyze which variables affect the variable that you are studying to which extent. But anyway, these numbers are not so easily interpretable as, for example, numbers in just regression models. But this is some natural way to at least to get any interpretation from my forest. So this is just an example of how these random forests work. I actually still not know why our prediction does not work for a particular row. I think that I will try to figure out it, and I will write you how to do it properly. But probably that's all that I wanted to discuss so far. So you can try to use trees for your data just to look at what happens. It can be interesting. Are there any questions?
Excuse me, I got some different numbers trying this variant function.
Yeah, that's normal because random forest is random.
Okay. Sorry.
When you create this forest, you have some randomization. You create random your samples, and you create different trees. And actually, this I think that this function is random itself, probably. Yes, no, yes. You see that when I rerun this function, I get a bit different numbers.
Yeah.
This is actually have explanation, because what this function do? In fact, it tries to remove some variable from your analysis, but when you have some forest, you cannot just simply remove a variable from analysis. You have to keep it in some way, but you try to make it uninformative. To do so, it just shuffles the content of this variable in such a way that this variable does not contain any information about the variable that you want to predict. And again, this shuffling is random procedure. So every time you run this function, you get slightly different result. But you see that the order of variables is preserved. So you can interpret it.
Yes, and in fact, these numbers are quite similar to yours. I see. Thank you. Sorry.
So are there other questions? Okay, so if there are no more questions, I think we can finish with the lecture. So this is the last lecture, the last class. But our course continues because you have your projects, and I will be happy to discuss your projects. So I will look at your proposals, and again, let me recall that we can arrange some consultations and discuss how it going on. So just do not hesitate to ask me if it is needed. So that's all for today. Thank you.
Thank you very much.
Thank you very much.
Bye.
Thank you.
Thank you very much. Thank you.
Bye.